Good morning. This is the eighth part in a series of seminars that I've given on LC mass spec unknown identifications using MS/MS libraries. And it's a little different than the others. This is another alternative when you can't use MS/MS libraries to identify things. One can use other databases. And so I call these identifications using Spectraless libraries. So the part 8's session is on the identification of unknowns with Spectraless libraries. The libraries are very good, and there might be over a million, between a million and 1.5 million type entries that you might find that have library spectra in MS/MS mode, but there are still a lot of unknowns that aren't in databases, and this is an alternative. And we've used it both for EI and MS/MS identifications when we couldn't find something in the library. And I want to emphasize that the things that I'll show you today, there's a lot more information in the handout that I've got on my website. So look at a little mass spec and sailing.wordpress.com, that's the address here. And you'll find some additional information besides what I present today. But I do have a table of contents for every one of the handouts I have for all the sessions. So take a look at those. All of them have more details, and take a look at the other sessions that we talked about in the past when we talk about using of the NIST software and the MS/MS databases. As this is, like I said, this is just an alternative. Those are better because they're more straightforward, but this could be a very powerful approach for identifying things in especially commercial mixtures as we've used at Eastman Chemical Company. So let's talk about the general overview of it. We need to identify compounds not found in commercial or crowdsourced libraries. And these compounds can still be readily identified with accurate mass data alone and LC MS/MS data and these large databases. And the ones I like the best, you start with accurate mass and you use either ChemSpider or SciFinder. See, this is much larger, 174 million entries in ChemSpider and 67 million entries in SciFinder. ChemSpider is a paid service, SciFinder is for free on the internet. You find your candidates, but of course, if you search by accurate mass or molecular formula, you'll probably find a lot of candidates. So somehow you have to narrow them down. And that's in the examples, I'll show you how one does that. And after you narrow them down, you have to confirm them somehow. So these, like I say, are primarily spectraless databases. There are some spectra in SciFinder, but in general, we're not searching by the spectrum. We're searching by either the molecular formula in the case of SciFinder or accurate mass, and in the case of ChemSpider, mainly by molecular formula. The other thing that we've called them originally, we stole the term from Donald Rumsfeld when he was talking about known unknowns in the weapons of mass destruction. And in my work, I've defined known unknowns that we first published in the Journal of Mass Spectrometry as compounds whose identities are known in the world, but not necessarily known to us. And we were using these large databases to find out what other people knew and correlate it to what we were seeing in our analyses. So, like I said, there's a lot more information about the pluses and the minuses and how you go about this in my handout. But today I'll just show you a few examples to illustrate how it might work for you. So let's start out with an example from SciFinder. SciFinder is a CAS registry product, very easy to use. It's an internet-based application, but you have to pay for it. So in this case, we were requested to identify a UV additive in the polymer. It was easily found in the LC chromatogram by its characteristic UV spectrum, so it was easy to decide what the customer wanted in the particular mixture. It was actually an extract of a polymer. And we determined the molecular formula by accurate mass and its isotope pattern to narrow it down. In this case, we started with the CAS registry that really is only easily searched by molecular formula. And you started, in this case, at that point in time, there were 65 million in the database when we were working on this problem. When you searched by C22, H29, N30, it narrowed it down to 2,256, but definitely not something that you could look through and decide to find what matched to your data. So we sorted by the number of references, and there were 2,059 that had references. And in those references, number one had 1,252 references. The number two hit sorted by references only had 20. So in these cases, we always start with the number one because in this case, it's a dramatic difference. We're looking for something that's commercially available. More than likely, people have been talking about it in the literature, and this will be what it is. And this is what the proposed structure was from the CAS SciFinder search. Very typical UV type compound that one would expect to be in a sample, but it wasn't in any of our MSMS or databases at that point in time. So what do you do then? Well, you start by interpretation of the mass spectrum. You can always search the NIST database and find similar structure to see how they fragment, but this is very logical. It loses a C2H4 by cracking off this group here or this group here. These type of molecules, of course, like to lose this C5H10 group, but it'll do it twice. And in our case, we were using acetonitrile, so there was an artifact in our spectrum where the acetonitrile from the solvent had reacted with one of the reagent ions, with one of the ions from the compound. So that was an artifact. And then finally, a small peak for the C5H11 itself. So a really nice fit for it that made me feel real confident that we had the identity. If you look at the UV spectrum, it's very characteristic of the UV absorber. And what we do a lot of time is infuse this material so you don't have to run deuterated material down your column. We just put it in a syringe, exchange it out with some deuterium oxide and count the number of deuteriums that exchange with the free OHs. And so we found that it did have one, which was consistent with the structure. And ultimately the customer, for his work, he needed to buy some to add to his polymer to see what it did for our material as opposed to what the competitor was doing, and it matched. But we felt really confident right initially that we had the proper structure. I had very little doubt that that was not the case. So let's talk about another SciFinder. This one was a little bit more of an obscure compound, and we did it a little differently. Again, at this point in time, there are about 65 million compounds in CAS registry. It's gone up to a huge number since that point in time. So we started with the molecular formula, C30H42O2. We found 264 possibilities. Well, not a huge number. If you get all the references for these compounds, there were 482 associated references for this 264 compounds. And when we refined this time, the customer was complaining something that was greenish yellow in his mixture or in his polymer that he was trying to make. And he was wondering why it was turning greenish yellow. So we just refined the search by greenish yellow. And there was only one reference that found it. And what was happening was he was using BHT and he wasn't getting the effect he liked. So he kept adding more. And the more he added, the more he got oxygen reacting with it to give this BHT dimer that you can see is very highly conjugated. And it was actually being used on a baby's diaper product. So you can see the customer in this case was very happy with the conclusion. The final example I'll talk about is ChemSpider. In this case, ChemSpider is good, especially for higher molecular weight things. As you get over 500 molecular weight, sometimes it gets hard to get an exact molecular formula, even using the isotope ratios and sample history. So in these cases, in many cases, the number of hits goes way down. If you look at the database population versus mass, it tails off. So searching, there are a lot more possibilities at high mass, but there are fewer organic compounds at higher mass. So in this case, you can do it by ChemSpider. SciFinder doesn't search by the more accurate mass plus or minus a tolerance, but ChemSpider does. In this case in time, at this point in time, ChemSpider had about 26 million entries. We searched by 783.520, and we allowed a mass error of 15 parts per million, which was reasonable for the instrument we were using at the time. That was an older instrument. And we sorted by the number of references, and we found 51 references associated with this mass to charge error range. And when you looked at those, there were 29 references for the number one hit, 5.2. So it fell off very fast. So again, we took a very close look to see if we can confirm the identity for number one. And it was this compound here that made a lot of sense for an additive in the polymer in the application that we were looking for. It's actually a competitive material, trying to figure out what they were doing. We initially confirmed it by MSMS fragmentation pattern. We could see that when we collided it in the source, this material is called Goodwright Ergonox 3114. And we were looking at the ammonium adduct, which essentially knocks off the ammonia to give the +1 to fragment. And when you did that, we got the very consistent ion one would suspect for 219.1743, where it would fall apart to this very stable fragment ion, that mass to charge ratio. And again, we took this material, we don't want to run it down the column with deuterium in our water for the eluent. That would just take a huge amount of deuterium oxide, be very expensive. But you can take this sample, even though it's a mixture, and mix it in a syringe, put it into an infusion syringe, and put it into the mass spectrometer. And we confirmed that it did have 3 protons. Again, it's just really easy to do the deuterium exchange experiment and see what the ion is shifted to. And then ultimately, this was confirmed again by purchase material because the customer wanted to try it his. But again, I was very, very confident about the identification initially, even without the customer buying the material. Though it's always good to have that confirmation. It makes you build confidence in your method. And as always, we added these things to our MSMS database. So the next time you just push the button and you find the identities. So I've got a lot of examples that we had from the literature and things that we published. So you might want to take a look at those, and they're all internet links they're actively hyperlinked. When you click on them, it takes you to the reference, whether in the literature or maybe on my website. So thanks. I hope you find this useful in your work. And again, the MSMS using the library searches with the NIST is always the preferred way if you can push the button and you find it. But this is an alternative method that we've had a lot of success with over the years, especially in commercial products. So I hope you might find it useful in your work, or some similar approach to searching other databases that are spectraless. Thanks for your attention, and take a look at the other 7 sessions